Okay, so right now we're going to look at a new method for solving these when getting a variable by itself is not very efficient. For example, if we tried to use substitution in this top one, we would end up with fractions once we got even the y by itself, which would make the substituting into the other equation a little bit clumsy. So the second method that we're going to use is called elimination. You may hear others refer to it as addition, both pretty good names for it. I prefer elimination because our goal is to eliminate one of the variables by adding the two equations together. That's why addition is also often used for this. Now in this first example, you may notice that when we add these two equations together, the x's cancel. So that will leave us with just one variable in one equation. So the 4x and the negative 4x cancels. 2y plus 3y is 5y. And 9 plus 16 is 25. And then we just solve for y, so y is equal to 5. And again, that means that 5 is the y-coordinate where this line and this line intersect. And then to find the x-coordinate of the point of intersection, we're going to take this 5 and substitute it back into one of these two equations. And it doesn't matter which one. I'm going to choose the top one. So I'm going to substitute 5 in for y, so 2 times 5 is 10. And then I'm going to solve it for x. Subtracting the 10 for x is equal to negative 1. So x is negative 1/4. And again, we can check. 4 times negative 1/4 is negative 1. 2 times 5 is 10. And when we add those two together, we do get 9. So it works for the first equation. The second equation, negative 4 times negative 1/4 is positive 1. 3 times 5 is 15. 1 plus 15 is in fact 16. So then I know that is a correct solution since it works in both equations. Now in D, the next example, the y's cancel when we add these two equations together. So we have negative 2x plus 5x, so that is 3x. The y's cancel. Negative 8 plus 20 is 12. Now when I divide by 3, I get x is equal to 4. And once again, that is the x-coordinate of the point of intersection. And we can plug that back into either equation. If I take this, I can plug it into the bottom one. 5 times 4 is 20. Minus 8y is equal to 20. Subtract 20 from both sides, so negative 8y is equal to 0. So therefore, y is 0. So the point 40 is a point of intersection. Again, I can check just to make sure it works. Negative 2 times 4 is negative 8, plus 8 times 0 is 0. That is, in fact, negative 8. So now back to checking. Worked in the first one. With the second one, 5 times 4 is 20. Minus 8 times 0 is 0. 20 minus, so I know that that is the correct solution. Now, in the next two examples, E and F, a bit of a problem is caused because if we add the two equations together right now, neither the x nor the y cancels. So what we need to do is force one of them to cancel. So the first thing you need to do is decide which variable you want to cancel. Well, in this case, just because the numbers are smaller, I'm going to choose to eliminate the x's. So what I need to do first is determine what number both 2 and 3 go into. Okay? Doesn't necessarily have to be the smallest one, but sometimes that works out best. And the number that both 2 and 3 go into, or a number, is 6. So I want 6x top, 6x on the bottom, and I want one of them to be negative. So I'm going to make the bottom one negative. If you want to make the top one negative, it really doesn't matter. So in this top equation, I want to turn the 2x into 6x. And in order to do that, I need to multiply by positive 3, because 3 times 2x is 6x. So I'm going to multiply the entire top equation by 3. So I have 6x plus 21y is equal to 3 times 4, which is 12. In the second equation, I need to turn the 3x into negative 6x, and in order to do that, I need to multiply the bottom equation by negative 2. So when I do that, I get negative 6x minus 10y is equal to positive 10. Now when I add these two equations together, the x's get eliminated. 21y minus 10y is 11y. 12 plus 10 is 22. So y now is equal to 2. That is the y-coordinate of the point of intersection. So to find the x-coordinate, I will take that 2 and plug it in for y in one of these two. Again, it doesn't matter which one. I'll choose the top. So 2x plus 7 times 2 is 14 is equal to 4. So now I solve this for x by subtracting the 14 and dividing by 2. So I get negative 5. And again, just to run a quick check, top equation, I have 2 times negative 5 plus 7 times 2 is in fact 4, so that works. Bottom one, 3 times negative 5 plus 5 times 2, that is in fact negative 5. So it checks, so I know that that is my solution. Now on to F. And once again, we can choose a variable to eliminate. This time, just for fun, because I am all about fun, I'm going to eliminate the y's this time. And I'm going to look at a number where both 7 and 2 go into, and that is 14. So I want to end up with 14y in both of those, but I want one of them to be positive, the other one to be negative. And it doesn't matter which one. So I want to turn 7y into 14y, and I do that by multiplying by 2. And I want to turn 2y into negative 14y by multiplying by negative 7. So when I do that, multiplying the entire top equation by 2, I get 6x plus 14y is equal to 30. And multiplying the entire bottom equation by negative 7, I get negative 35x minus 14y is equal to positive 28. Negative 7 times negative 4. Now when I add these two equations together, the y's get eliminated. 6x and negative 35x is negative 29x is equal to 58. And then x is equal to negative 2. Again, that is the x-coordinate of the point of intersection of these two lines. I'm going to put that into one of these two. I'm going to choose the top one. 3 times negative 2 is negative 6. Plus 7y is equal to 15. Add the 6, so 7y is equal to 21. So y is 3. And again, a quick check. Negative 6 plus 21 is in fact 15. Negative 10 plus 6 is in fact negative 4. that is a solution to both, therefore it is a solution to the system. And these two hopefully will look familiar to you. They are actually examples A and B. I'm just going to show you in examples A and B we use substitution to solve these. Now we're going to solve them using elimination. Now to make things a little bit easier, in this one you can eliminate the x, but I'm going to choose to eliminate the y because in order to eliminate the y, a number that both 4 and 1 go into is 4. So I just want to turn the bottom one into negative 4. Why? I'm going to keep the top equation exactly the same. I don't have to change anything. The bottom one, how do I turn the y into negative 4y? By multiplying by negative 4. So I have negative 8x minus a 4y equals negative 40. Add the two together, the y's do cancel, so I'm in good shape. 3x and negative 8x is negative 5x. 12 and negative 40 is negative 28. So x is 28 fifths, and that is what we got before, I believe. So I probably won't check this one since we did before. Now I'm going to take this value and plug it in for x in one of the ones. I'm going to choose the bottom one. 2 times 28 fifths is 56 fifths, plus y is equal to 10. So then y, I'm going to subtract 56 fifths from both sides. Well, 10, I need a common denominator, is the same as 50 fifths. So I get negative 6 fifths for the y value. Now for h, I'm going to choose to eliminate the x's. That way I only have to multiply one equation by something. So I'm going to keep the bottom one the same. And I need to end up with 2x on the top. Well, in order to turn x into 2x, I need to multiply that top equation by 2. So I end up with 2x plus 6y is equal to 10. Add them together, I end up with 2y is equal to 5. So y is 5 halves. That is the y coordinate of the point of intersection, and I'm going to substitute that into one of these. I'm going to choose the top. So I have x plus 3 times 5 halves is 15 halves. That's equal to 5. So I'm going to subtract 15 halves from both sides. Well, 5 is 10 halves. So I end up with negative 5 halves for the x value, which is what we had before. In the next video, we're going to look at some special situations with these systems of solutions, or systems of equations.